So chapter 8 is going to be our first look here at energy in the body. And you've probably seen this word before, metabolism. A lot of times we use it in terms of energy and food, and people have fast metabolism or slow metabolism, and that's not really what it means in biology. Your metabolism is just the total sum, all of the chemical reactions in your body. So if you added up every single chemical reaction in your body, that's just your metabolism. And some chemical reactions require energy, and some chemical reactions release energy. So metabolism is related to the energy that your body kind of uses or releases, but it's just the sum total of all of your reactions. Every process in our body typically has a metabolic pathway. So we've seen pathways before where they have multiple steps in a row to get from a starting place to some kind of ending product or response. And in the case of metabolic pathways, we're going to see, again, multiple steps. And the reason we have multiple steps is because it's much more energy efficient to either take a large molecule and break it apart piece by piece, gather energy at every step, or to do the opposite, to build particles using small steps that each step only requires a little bit of energy input. So here's the most generic ever metabolic pathway. We literally have some chemical reagents. So these would be molecules, A, B, C, D. The goal of this metabolic pathway is to get from molecule A to molecule D. But you can't go directly from A to D. That's not how the metabolism of our body works. Our body works in small steps. So you need enzyme 1 to get from reactant A to product B. You need enzyme 2 to get from reactant B to product C. And then you need enzyme 3 to get from reactant C to product D, which is the ultimate goal of this specific pathway. So notice that every time we have an arrow for our chemical reaction, there's typically going to be an enzyme involved. We're not always going to draw the enzyme. Sometimes we'll point them out, but it's good to remember that they're always there. The enzymes help speed up the reactions. They don't actually change the energetics, they just make the reaction go faster so that it's efficient for our body. There's two main types of pathways. A catabolic is going to release energy by braking. So if you think about that, that sounds a lot like hydrolysis. So hydrolysis is one example of a catabolic pathway. It's going to take something large and complex, like maybe something big like starch, and break it down into simpler compounds, so things like glucose. So we're going from big to small. And this is usually going to provide energy for the body. Another example here is cellular respiration, which is going to take glucose, which is C6, carbon 6, H12O6, and it's going to, amongst other reactants and products, break the glucose carbons into 6 carbon dioxide. So we're going to go from one molecule with 6 carbons to 6 molecules with only 1 carbon each. So we're going from relatively large to relatively small. And when we do this, it's going to provide energy for the body. So it's going to actually release energy from these reactions. The opposite of this would be an anabolic pathway. This is going to consume energy, so this is going to require energy to go. And it's going to do the opposite, it's going to build. So an example of this would be dehydration synthesis, which is the process for protein synthesis, where we would take individual amino acids and stick them together to make larger chains. The opposite of cellular respiration is photosynthesis, which is going to essentially take carbon from the atmosphere and turn it into glucose. So we're going to do the opposite of this. Take something relatively small and turn it into something relatively big. And this kind of thing is always going to require energy. So every time we build a bond, we have to put in some ATP to build something more complex. And it's not always ATP. Photosynthesis uses energy from the sun to power plants to be able to build complex sugars from carbon in the air. What is energy? Energy is the capacity to cause change. So when we cause change in the body, this is doing work. So we're going to have the capacity to do biological work. And this exists in different forms. Kinetic energy is the energy of motion. So if I were to hold a pen and then let it fall, while it is moving, it has kinetic energy. Usually, if you're in a physics class, you might see a picture of a kid on a swing where the swing goes back and forth. And when the swing is moving back to forth, it has kinetic energy. In our chemicals, so in our molecules, the way that we measure kinetic energy is the random movement of molecules. So every molecule vibrates. The overall measurement of that would be the temperature. So heat is just the transfer of thermal energy from one molecule to the next. So the more heat there is, the more motion, the more thermal random motion of molecules, the higher the temperature. So temperature is actually just a measurement of the kinetic energy of individual molecules. The other type of energy we're usually concerned with is potential energy. So this is energy that is stored either based on location or structure. So when the swing is all the way back and it's about to swing down, but it hasn't started moving yet, so it's not moving, the swing has a high potential energy. And then as soon as it begins to move, the potential energy gets transformed into kinetic energy. But we're looking at things on a molecular level in this chapter. So the potential energy of our molecules is not really where the location of the molecule is, it's the structure. So the chemical bonds that they form is the physical structure of the molecule, and that is where the potential energy is stored. So think about something like ATP. It's got 3 phosphates stuck together, and those phosphates have a very negative charge. Putting 3 negative phosphates very close to each other is going to be a very strained structure. So when you break these and release a phosphate, it's actually going to reduce the potential energy, and so energy gets released. So the chemical energy is just potential energy. So when we're talking about free energy or the energy in our reactions, we're talking about chemical or potential energy that is available to be released. And we can't continue to talk about energy until we learn the laws of thermodynamics. So the very first law is that the energy of the universe is constant. Another way to say this is that it cannot be created or destroyed. If you find a test question and it has the words create energy or destroy energy, that answer is wrong. The energy in the universe cannot be made or destroyed. The only thing we can do is transfer it from one place to another. So for example, transfer it from the sun to the earth. And we can transform it into one type of energy or another. So we can take light energy from the sun, and then plants can transform that into chemical energy in the form of glucose. This is called the principle of the conservation of energy. So the amount of energy that goes into a system is exactly equal to the amount of energy that comes out of a system. It just may look different and it might be in a different form, but it's the same amount. So the second law of thermodynamics is that every energy transfer increases the entropy of the universe. Another way to say this is that every time we use energy, so every time we transfer it from one place to another, or transform it from one type to another, some of it gets lost as heat. Energy transfer is not efficient. So what is entropy? Entropy is disorder or randomness. Randomness is just disorganization. If you leave something alone, it will disperse randomly to fill all of the available space, like diffusion. Diffusion is a great example of entropy. So diffusion does not require energy. If you drop a drop of food coloring into a glass of water and just leave it, over time, the entropy will increase. The molecules of the food coloring will randomly disperse throughout the glass of water, and the entropy will increase. Types of reactions that increase entropy by creating randomness and disorder, by taking big things and breaking them apart, are going to release energy. It could be in the form of ATP, and it's always going to involve some energy as heat. So this bear ate that fish, and he's used the nutrients from the fish to turn that into ATP in the process of cellular respiration. And as the bear does that, some energy gets stored as ATP and used for the bear. Some energy gets lost as heat, because every single step on the metabolic pathway loses some energy as heat. What does the word spontaneous mean? Spontaneous in real life might mean like, oh, just doing something on a whim, or not thinking before you do something. But in biology, spontaneous is any process that does not occur with energy. So it will occur without the input of energy. For example, all of passive transport is spontaneous. It just happens if the molecules are there. You don't need any energy. The reason this happens is because it increases the entropy of the universe. Diffusion of molecules from a tightly packed place to a spread out randomness increases the entropy of your glass of water. A lot of times we think about spontaneous processes being fast. So spontaneous combustion, right? We think of that as something that would be quick. A spontaneous process does not have to be quick. It can be fast or it can be slow. The only requirement for something to be spontaneous is that it does not require energy input. So a common misunderstanding of the second law of thermodynamics is that when we make complex organisms, well, doesn't that violate the second law of thermodynamics because we're taking things that were random and building complex molecules or organisms? And this does not, because the process of building a complex organism will actually create more entropy than it removes. Let's use an example of organizing your room, right? So let's say that you have let entropy control your bedroom and it is an absolute mess. You have to go through and clean it. Well, the process of cleaning your bedroom would remove entropy from the universe because you are organizing things in a non-random way and putting them away where they belong. But every process increases the entropy of the universe always. So in the process of you cleaning up, you have to walk and move and bend over and push things around. And every time you move something, your body releases heat in chemical reactions, burning energy to do the movement. And so the sum total is that even though you have taken something messy and organized it into maybe a very complex cleaning system, the process of you cleaning creates more entropy. Entropy cannot be used to do work. Entropy is just heat that gets lost and there's no way to get it back. So free energy is the energy that your body can actually use to do work. So this is the ATP that has the capacity to do biological things. We have an equation here. I'm not going to make you do any actual math, but I do want you to understand this. So delta G is our free energy, and delta G is the total energy minus the entropy. So it's the total energy of a system minus the energy that gets lost as heat. Free energy changes during all processes, from the beginning of a process to the end of a process. So the delta here just means the change in, so delta G means the change in free energy. If delta G is negative, so that means that the change in G is less than 0. This number is a negative number. That is going to be a spontaneous process that is going to release energy. So we can kind of see this drawing an energy graph. So our G is going to be over here. This is free energy. We'll do a bar graph with our reactants as our starting materials and our products as our finishing materials. If the reactants have a very high free energy and the products have a lower free energy, the difference between these, when we go from a big number to a small number, is going to give me, basically we're going down a hill, right? We're going to get a negative delta G. So this will be something that is spontaneous. If the delta G is 0 or positive, so if delta G is greater than or equal to 0, it is not spontaneous. So this is going to require energy to go. So for example, here's our G. We start with our reactants and with products. If the reactant's energy is lower than the product energy, think about this as kind of having to go up a hill. This amount of energy has to go it has to be added to this, even if they were the same, if delta G was 0, if they were the same. This is going to give me a positive number, and this is going to require ATP. These types of reactions have specific names. We have exergonic. Exer means out. So it is going to release free energy. So here's the same type of graph. Over here is the free energy, that's G. The bottom is the progress of the reactants. So we have the reactants at the beginning, the products at the end. The amount of energy released is from what the reactants had to what the products had. So this is my delta G. And because the energy is being released, it's going to be negative. So this is an exergonic reaction. We also call this catabolic and spontaneous. Endo means inside. This means that the energy is going to have to be added in. So an endergonic reaction is going to absorb energy. So this is going to be absorbing energy in the form of sunlight or and energy in the form of ATP. We are going to require some kind of energy input. So my endergonic reaction is down here. Again, free energy is G. My reactants have a low free energy. My products have a high free energy. So the amount of energy that I have to put in is this difference. So this is going to be this is my delta G. That's the change from here to here. And this is going to be positive in this case because we have to put energy into it. So an endergonic reaction is going to be an anabolic or building reaction, and it is going to be non-spontaneous. So this would be, for example, active transport, where you have to use ATP in order for the sodium potassium to pump to move molecules across the membrane. Our cells do not exist in a state of equilibrium. They are considered open systems. So we are having constant flow of materials. The metabolism and the reactions within our cell never actually stop. We're always putting molecules in, and we're always getting molecules out. So, for example, you could think of putting in glucose and getting out ATP in the process of cellular respiration. So this is a defining feature of life. So your entire body is a system. Each individual cell is a system. You're a bunch of systems within systems. And so the energy and the molecules in our body are constantly moving. The vast majority of the work that our bodies and our cells do is going to be powered through ATP. For animals specifically, we're not doing photosynthesis, so we're not using solar energy, we're using ATP. And the different types of works that we're going to see are going to be chemical work. So ATP is often coupled with endergonic or anabolic reactions to help power them so that they actually go, because we do need to build things that cost energy. Transport work, so think active and passive transport. So active transport would require energy to pump substances across membranes in the direction of going against their concentration gradient. And then physical or mechanical work, such as contracting muscles, so contracting your heart, physically moving your pen right now so that you can take notes, are all going to require muscle contraction, which every muscle contraction requires lots of ATP. So this is done in a process called energy coupling, where we are going to couple a endergonic reaction, which is the one that requires ATP, with an exergonic process, which is usually just taking ATP and removing a phosphate. So at this point, you should know the structure of ATP, adenosine triphosphate, that we've got an adenine, we've got a ribose sugar. This is a nucleic acid. And we have 3 phosphate groups. Look at those negatives. lots of negative values, so negative, negative, -2. And those negatives are very close together. They're very close. So when we break this bond, the chemical free energy goes down. So we have, here's our free energy graph. We have ATP and ADP. ATP has a high free energy and ADP has a low free energy. So when we do this, we're going to release energy, and it's going to allow us to take that energy and use it to power other reactions. And this usually happens by creating some kind of phosphorylated intermediate. So here is my ATP. This is just going to be an active transport molecule, so this looks like just a generic carrier where we're going to move these yellow circles from an area of low concentration to high concentration. So what happens is the phosphate breaks off of the ATP and physically sticks to this molecule. This is my intermediate. And the physical connection of the phosphate changes its shape, which allows it to move. And then when that releases, it's going to change its shape again. The overall result is that the ATP gets broken down into ADP plus a phosphate. And again, phosphate I just means inorganic because it's no longer attached to an organic molecule. The great thing about ATP is that ATP is a renewable resource. So it is regenerating. We can regenerate it in our body. All we have to do to regenerate it is take ADP and a phosphate, put some energy in from an exergonic resource like cellular respiration, and we can use that to build new ATP molecules. And then those ATP molecules can be used to release energy for more cellular work, so transport or mechanical or chemical work within the cell, which leaves us again with ADP and phosphates. And so this is a renewable ATP cycle where as long as we are going to continue consuming glucose and able to continue doing cellular respiration, we can keep making energy for our body and keep performing the work that our body needs to do.